In this video, we will talk about a problem in the Putnam Mathematical Competition 2005. The problem states as follows. Let H be an n by n matrix, all of whose entries are plus minus 1 and whose rows are mutually orthogonal. The matrices satisfying this condition will be called a Hadamad matrix. Now suppose further, H has an A by B submatrix whose entries are all 1. Then we are asked to show that A times B is less than or equal to n. So that is a problem. We're going to talk about two solutions to this problem. Solution number 1 uses the idea of inner products. This solution goes as follows. Choose a set of A rows. Here this A is this number A. And we denote them by R1 through RA. We put arrows above them to denote that they are arrays, not just numbers. So how do we choose them? We choose them so that they contain a submatrix whose entries are all 1. For example, if your matrix H looks like this, so there are some 1s which forms your submatrix, A by B submatrix. In this case, A is equal to 2 and B is equal to 3. So there are 2 rows and 3 columns. And all the other entries are plus minus 1. So everything else is plus or minus 1. Now we look at those 2 rows. 2 rows R1 and R2 contain a submatrix whose entries are all 1, as indicated in the picture. Now since the rows of H are mutually orthogonal, we know Ri dot product with Rj will be equal to 0 if I is not equal to j, and is equal to n if I is equal to j. When I is equal to j, they are identical because each entry is plus or minus 1. So the dot product of Ri with itself must be n, the sum of squares of all of its entries, which is just n. And we mark this equation by star. Now, this inequality will be obtained by looking at the following quantity in 2 ways. We'll look at this quantity S, which is the inner product of R1 plus R2 plus all the way RA, dot product with itself in two ways. First, if you just look at this equation, this relation immediately gives you that S is equal to A times N, because there are A terms, and Ri times Rj, if I is not equal to J, is 0. Otherwise, it is N. So this gives you A times N. So this is one way to look at it. Now, on the other hand, the vector R1 plus R2 plus the RA, if we denote by components x1, x2, all the way to xn, we'll notice that there are at least b out of its n components equal to A. Why is that so? This is because if you look at those A rows, as in this picture, A is equal to 2. We look at those A rows, and those components are the sum of components in R1 through RA. So what we are doing is that we are summing up at once in those at least B components. Because for this submatrix, there are B columns, and all the entries in the submatrix are equal to 1. So we are just summing up once. And their sum will be precisely equal to the number of rows, which is A. So there are at least B out of its n components equal to A. So the second way of looking at this quantity is as follows. This S, which is the dot product of this vector with itself, will be bigger or equal to, because there are at least B out of its n components equal to A. So this quantity will be at least B times A squared. A squared comes from, when you take this dot product, the components whose value are equal to A will be squared. So there should be an A squared, not just A. Now, combining 1 and 2, we obtain from 1 you get this S is equal to AN. But from 2 you get S is bigger or equal to B times A squared. So by canceling A, you get N greater or equal to B times A, which is the inequality we want. So this is the end of the solution number 1. We prove this inequality.